Alright guys, so let's get started. So let's see what we did last time. So last time I think I returned the exams, and then we kind of continue with this chapter over here, which is the second principle of thermodynamics and entropy. Alright, so I think you know that why do we study this? Because there are some limitations to this equation. One is that it says it's 100% efficient. We said that we already took care of that. The other one is that the equal sign means that the equal sign can be read from both sides, no? And we know that some processes are reversible and some other ones will be irreversible. So in order to take that effect into account, we define the Carnot principles, which basically the ones say that the efficiency of an irreversible cycle is always lower than the efficiency of the reversible cycle. And the second one that said that the efficiency only depends on the temperature of the reservoirs and not the substance. So basically I kind of did this and I said this is the ratio which is really important over here. Okay, so this is the exam. And then we kept going with the class notes. We say that we know everything about this type of Carnot cycle. All right. So what about we take a general cycle and we divide it into one finite number of Carnot cycles. All right. So we did that. So we did for the first cycle. We got this expression over here, which basically we said. So we did the same thing for the second cycle. And you could do something similar for every single cycle. So if you add them all together, you know that adding things together is the same thing. Summation sign is the same thing as the integral. Okay. So if we add all of them, we find out what? That for reversible cycle, which we know is the Carnot cycle because this one is reversible, no? Yeah. So if each one is reversible, all of them will be reversible. So we ended up with that definition. Okay. Now I should be more. I mean, it's just an inequality sign, but I'm going to do it very quick without going into too many details because the derivation is not important. So that's where we stop. All right, so that was page 101. So this will be page 102. This is ES305. Today is 4/5, yeah. 18, and this would be lecture 17, 18. You're probably right. Just double check. 18. It looks like, yeah. The last time was 17. Alright, so basically this is where we stop, okay? Over here. Now, this is not 100% correct, but it's correct, okay? Let's just say here, recalling the Carnot first principle. What does that one say? Is that the efficiency of the reversible cycle always lower than the efficiency of the irreversible cycle, okay? Okay, so it can be, I say that, but it's not really complicated, okay? It's 3 lines, but I don't see why we're going to do it. So it can be derived that for an irreversible cycle will be lower than 0. Because if it's 0 for the reversible, it should be lower than 0 for the irreversible, no? Okay? You can show it mathematically, but it's 3 lines, and then You look at me like that because there's an equal sign, so you need a negative sign, so you need to change the direction of the inequality. I think it's just easier to just understand the concept, no? Okay? So summary. So this is what is known as the Carnot. Some people call it Carnot theorem, but sometimes it's called as the Carnot inequality, which I think is more appropriate because delta Q over T. So we're going to have here two cases. If it's equal to 0 is reversible, and if it's lower than 0 it is irreversible. Okay, so you see it's hard to have a physical understanding of what is delta Q over T. So what is change of heat divided by temperature, no? I mean, it's personally, if you ask me, give me a physical interpretation of that, I wouldn't know what to tell you, okay? But I know what it's used for, all right? So basically, it's going to tell you if a system is reversible or irreversible. So it's really a way to measure how you are using the energy. Okay? So let's go to the textbook, because I know they do 2 chapters on this, and let me see exactly what they do. Because the first one, if I remember right, is kind of conceptual, and then they go really into the problems for closed system and open systems. So I think, let's see. So we did 2, 3, 5. Okay, the second law of thermodynamics using entropy. Okay, so I guess they do it that way. So let me see exactly what they did over here. Straight to the problems. See what we want us to do. Okay, this is the part that I'm interested. Problems. Okay, let's do 5, 5. I don't know, just like that, because that's a nice figure, and see what we can do with it. So let's see if I can make this that we can see both things on the screen. So maybe I can make it work. Will that work over here? All right. Page 103. exercise. Will be the problem 5.5 in the textbook. Alright, so let's see. As shown on figure 5.5, a reversible cycle R and an irreversible power cycle I operate between the same two hot and cold thermal reservoirs. Cycle irreversible has a thermal efficiency equal to 1/3 of the thermal efficiency of the cycle of R. Okay, so let's do the figure. Alright, so it looks like we kind of have like a hot reservoir over here. We're gonna have a cold reservoir over here, and in between basically you have a reversible cycle and an irreversible cycle. So this one is going to produce a work of W reversible, this one of W irreversible. So they call this one here Q hot, this one will be Q prime hot. This one, okay, is Q cold. I'm going to complicate the notation, and this one would be Q prime cold. Okay, the but W, okay, but that we know those things. So what else do they say is that the thermal efficiency of the irreversible equals 1/3 of the reversible cycle. So A, if each cycle receives the same amount of energy by heat transfer from the hot reservoir, determine which cycle develops greater work okay, discharger greater energy by heat transfer to the reservoir. Wait, are they serious? I mean, I don't know, but so I don't know exactly how to do the answer, but okay, so which one is going to produce more, develops greater network, the reversible or irreversible? Should be the reversible, no? One, because we say that the efficiency of the reversible is always higher than the efficiency of the irreversible, no? So just for that reason, and we also say in one other statement of the Carnot principle is that says that there is no more efficient power cycle than a Carnot cycle, no? Operating between the two same temperature reservoirs. So let me look at the solution exactly what I want us to do, but I think that one is, I would just say by Carnot principle, and then determine which cycle develops, so discharger greater energy by heat transfer to the cold reservoir. So this time, which one will discharge more energy? The reversible or the irreversible? If you look at the solution here of the textbook, when they have, can I show that? No. Over here, that might be will give you the answer, no? If Q is the same, no? Because the same temperature reservoir, but this one produces more work than this one, which one will be rejecting more heat to the outside? The irreversible, no? So basically means that the reversible cycle is going to waste less energy than the irreversible, no? Okay? Okay. I don't know how to answer those things. I mean, it's things. Okay, so let's say A, we can just say WR higher than work irreversible because a reversible cycle is the ideal power cycle in this case. Part 2 means which one is putting less or more energy by heat transfer into the cold reservoir. So we know that QC, we can just copy what I have over here, QC equal QH minus WR, and Q prime cold equal Q prime H minus W irreversible. And what do we know about this? I mean, about both cases is that QH equal Q prime H, no? And we know that WR is higher than W irreversible. So if we combine all this, what does that mean? That Q prime C will be higher than QC. Okay, that's not the kind of problems I was thinking of, but I thought it would ask me something, a bit of numbers, but okay. So let's see part B. If each cycle develops the same network. Okay, so this one might be more interesting. So this time we have WR equal to WI for reversible and irreversible. Develop the same network. Determine which cycle receives greater energy by heat transfer from the hot reservoir. Okay, so if we do that, basically what we could rewrite this equation here as what? We know that W for any case would be equal to what? Q hot minus Q cold, no? So from this equation we could write down, let me just make some space, Q hot will be equal to what? Work plus Q sub C. Yeah? So this will be the general equation. General equation. So in our case, we could just rewrite that Q hot equal WR plus Q sub C, and that Q prime H equal W C. So remember, WR, reversible and irreversible are equal, no? So everything will depend on these two. So what do we say at the beginning? Is that which one is harder, Q sub C or Q prime sub C? Which one will be throwing more heat into the cold reservoir? Q prime, no? So that means at the end, which one will be removing more heat from the hot reservoir? The irreversible, no? Okay, so in this case, you can say that because, let me change the color. Because Q prime cold higher than QC, then we have that Q prime H will always be higher than QH. answer the second question then. Maybe we made that assumption there that is not correct. Okay, let me look at something. Let me take another page, because it's something we haven't been using at all over here, no? I mean, let's see. I don't know. We haven't been using the fact that the efficiencies, correct? All right. So let's see what will happen over here. Let's see if we can come up with something because of that.
Professor, for part one, if we set them both equal to work, so work R.
For this part, you say?
Yeah.
Yeah, but I'm assuming here, which I don't know. This is what they ask us to prove on the second part, I guess. You see, discharge greater energy by heat transfer to the cold reservoir.
What did? Oh no, something about the first part.
Okay.
The first part, wouldn't the reversible process take more energy from the hot reservoir since work in the same and QC's?
Wait. Okay. Let's go back again. Okay. So part A is develops graded work. So the graded work will be developed by the reversible.
Oh, I'm sorry. I'm talking about part B, number one.
Okay. This one.
Yeah.
Okay. So this one. Okay, but I'm going to redo this one because if you read on the prompt, this is what they ask you to prove on the second part. Discharge greater energy by heat transfer to the core reservoir. So I'm just trying to take a different approach, okay? So let's see. If I take a different approach here, just take a different piece of paper to see what we can come up with. So I don't know where to go, okay? I'm kind of solving it, going blind a little bit. So let's see, the efficiency. Again, I'm working on the side, you see, on a little piece of paper because I don't know exactly what to do. So what is the general definition of the efficiency? Is whatever you get out divided by whatever you get in, no? So now we know this is equal to Q hot minus Q cold divided by Q hot. So we could say that this is equal to 1 minus Q. Let's put it this way. I don't know which one we're going to need. So if we say that the reversible is W reversible over QH, and this is equal 1/3 of the irreversible over Q prime H, no? Wait, let me read. Don't they say that the thermal efficiency, so cycle I, which is irreversible, has a thermal efficiency equal to 1/3 of the thermal efficiency of the cycle of R. Yeah. So this would be 1/3. So what can we conclude for this? So we know that WR equal to the irreversible, so that will give us 1/3 of W over QH equal W over QH. So it will be Q prime. So from here we get what? Q prime H equal 3QH, no? Basically we get the same conclusion that the one before, but I kind of prove it out here, no? Yep. So if you want, just remove this over here, remove this part over here. Sorry, let me go back. Remove this part over here, and let's do it together. And on the next page we can say that because, and we just copy what we just did, the general expression for the efficiency is means that the reversible here is 1/3 Q prime H, because on the initial problem we had that the efficiency of the irreversible is 1/3 of the efficiency of the reversible. So now we do this is equal to 1/3 of W over QH equal W over Q prime H, because you know that W reversible equal to the work to the reversible equal to the work. So this would cancel. So at the end we get that Q prime H equals 3QH. So which basically means what? That in order to have the same efficiency, for the two to create the same amount, not to have the same efficiency, sorry, for both cycles to produce the same amount of work, you need to extract 3 times more heat from the irreversible than the reversible, no? Okay? So basically you are using 3 times more energy than for the reversible. You go to that figure, you are removing 3 times more from this one, no? From here. Yep? In order to get the same work. Alright? So now, what is part B? Or part 2? Is that they want us to prove, what is it? Discharges greater energy by heat transfer to the cold reservoir. So, I guess here we can do, let me check over here first. I'm pretty sure it can be done that way, but let me try. We have this Q cold. So this one will be equal to each other, because we know that WR equal WI, H minus QC, QC. So that's not going to do anything. That's what I was trying to do, but what happens is that these QC are going to cancel each one on each side, no? Q prime H minus QC equal. That's what I was trying to do, but no. Oh, okay. Or maybe we can come here and say QH equal W minus Q sub C. No. Alright, the other way around. Q sub C will be equal to Q sub H minus the work and we know, we just proved that Q sub H is 3Q. Okay, so I think we got it. So here we can say that we know that work equal Q sub H minus Q sub C. So from here we can say that Q sub C equal to what? Q sub H minus work. So if this is our general equation, now we can write what? We can write that Q prime C equal to Q sub H, Q prime H minus work of the irreversible But I'm going to go a little bit faster. We know this is equal to W, no? Because in all these parts, what do we have? Work reversible equal to the irreversible. And if we do the same thing for the other one, we have Q sub C equal to QH minus work reversible, which is this one. Yep. Now, what we did just prove? That Q prime H is equal to what? 3QH. I'm going to put it over here because Q prime H equals 3QH. And then we have here that Q sub C will be equal to what? Q sub H minus W. So which one removes more heat to the cold reservoir? Which one of these two is higher? Q prime C, no? Okay. So Q prime C higher than QC. Okay, guys, so you see that I don't know the solution of the problems by memory, no? When I know something, what do? I go to my little piece of paper, no? And try stuff on the side. Okay? Don't think that I know everything at once, okay? I need to try things out. So let's see, there's something else over here that could be interesting. I mean, you see, those are basically conceptual. There's not really numbers. About this one, but let's try to do it, okay? I read it and I don't really understand it, so let's do it, okay? That way we have to understand it together. The 514, okay? When I read it, let's see what 514 is. Again, you see I pick a lot of problems by the figure, so 514. So let's do the figure. We do it together. Let's see. All right. So 514. So it looks like there is a hot reservoir, which we call the dwelling, and this is a heat pump. And so what do you say? Consisting of a reversible power cycle driving a reversible heat pump. Okay, so it's a little bit tricky, this one. I might do a little bit different, okay, the figure. Or maybe not. It's going to be too confusing. Change. Right, let's do the same way. To me, it looks confusing, okay, the way it is over here. Let's see if I would change it. Let's do the same thing and we work with it. So it looks like we have a power cycle over here. That to me is receiving heat by some type of air. So they put over here this as Q sub S. And this is removing energy Q sub 1 into some type of reservoir over here. So for this one, it's really the cold reservoir for the power cycle, but it's going to be confusing me here. So basically what's going to happen? So this is going to produce what? Work, no? So the work is going to produce is being transmitted into a shaft. So if you want, this is the work produced by the power cycle, and is going to go into a heat pump that operates between Q sub 0 over here so this is another reservoir at temperature T naught, so this is T dwelling. Obviously T dwelling needs to be higher than T naught, obviously that makes sense, and Ts is higher than Td, obviously because it's the hot reservoir. Okay, all right. Kind of confusing all this stuff, but and this is Q2. So let's see. The power cycle receives Q sub S by heat transfer at Ts from a high temperature source and delivers Q1 to a dwelling at Td. The heat pump receives Q naught. Okay, I got all this part. Obtain an expression for the ratio of the total heating provided to the dwelling to the heat transfer supply from the high temperature source. Okay, so is that expression there, Q1 plus Q2? So obtain an expression for the ratio of the total heating provided to the dwelling. Oh, okay, so that's Q1, correct, plus Q2 okay, over Qs. Yes?
What is the subscript of the Q into the heat pump?
This one here?
On that.
This one? Q sub 0. So again, that's one of those problems that so find an expression, so expression for this in terms of Ts, Td, and T sub 0 or T naught. So I think the important word over here is that they are reversible. So if they are reversible, the efficiency is going to be in function of the temperature. Is that what they want us to do? Alright, so I have no idea how to solve this one again. So what I'm going to do is what? Take a little piece of paper. Okay? So you see a little bit of brainstorming, no? So let's see. When I look at this, the only thing I'm thinking is because they say that everything is reversible. Okay, I'm just saying out loud what I'm thinking, okay? That doesn't mean it's going to be the right way to do it. So not everything you get the answer right away. So it's reversible, so what would be the efficiency of the power cycle? of this one over here? Generally, is whatever you get out. Let's say the work by whatever you put in, no? Generally, is Q hot. So in this case, that would be equal to what? So that would be work, which is not given over here, even though I put it on my figure. And what is the Q hot for this one? QS, no? And the work here will be equal to what? QS minus Q1, no? The hot minus the cold. Yes? Okay, that's what I'm thinking, okay? That means you do it this way. So I'm thinking this about the first one. So this will be the power. Then the efficiency of the heat pump. What will be the efficiency of the heat pump? Is whatever you get in divided by whatever you get out. So what do you get out of the heat pump? Q2. And what do you put in? The work. So in this case you get Q sub 2 divided by what? Q2 minus Q naught. Okay, so I'm just thinking, so out of these two, maybe I can rewrite the work as being equal to what? QS minus Q1, and this should be equal to what? Q2 minus Q naught. Sorry, and this would be equal to what? Maybe T sub S minus T1 divided by TS, and this would be T2 divided T2 minus T naught. So sorry, I could write this work equal to what? TS minus T1. Yeah, but I need to Q1 plus Q2. That's why okay. So we know this stuff. So alright, see. Not good. Sorry for that. Let me go back to the other one. So QS minus Q1 equal Q2 minus Q naught. So from this expression I could get what? That, trying to look at the top one, so Q1 plus Q2 will be equal to what? If I move this one to the other side, I get Q1 plus Q2 equal to QS plus Q naught. So does that help a lot? Or no? So I guess what on TS, what is TD? So okay, so alright, so if I look at this prime, if I do this now, what would I get? I would get Q1 plus Q2, and I'm kind of thinking this should be proportional to what? TS plus T naught, no? So that gives us TS, T naught, but we don't have TD on the expression. TD is on which one? Did I do? I'm just trying to write, you see the top here, they ask us Q1 plus Q2, no? So just trying to find an expression for Q1 and Q2. QS plus Q naught. And then, oh, QS. What is QS? QS is is not T2. QS will be TS in this case.
Q1 and
Okay, so you got one expression. What could be the other one? They don't tell us anything else. Well, let's do a little bit of cheating. 514. So what did they do? Let's put screen on. Okay, so let's see, they kill me over here. Let's see what they do, because I don't. Q1 plus Q2 equal to QS plus Q0, no? Q1 plus Q2 divided by, what do we divide by, QS or Q0? By QS equal 1 plus Q1 plus QS. Applying the second law, okay, now I see what they have done. Then they do Q1 over QS equals TD over TS, no? Yeah. They get Q1. Yeah, I see what they're doing now, but are we doing this kind of the same? So in our way, we need to find QS. And QS given this. Yeah, but we cannot substitute it that way. We need to find an expression. Because from that one, it looks like QS will be equal to what? Will be equal to TS times, will be equal to Q1 times TS divided by TD. It's not that you can say QS equal TS, no? So we could use what we have, but then we have a problem with the Q1. I'm just trying to find a way to do it without changing what we have done so far. Alright, let me just do it the way they do it, and that way we get done with it. Okay, so basically what I'm doing is this. So, what they do, what they call the energy balance, is that what they're trying to say is that the amount of energy going inside the system needs to be equal to the amount of energy going out of the system, no? Alright? So for the, let's say for the whole system, so maybe let me do a figure. with this. The whole system, we can say energy in equal energy out. So you're gonna have what? QS, I think is what they say here, QS plus Q naught equal to Q1 plus Q2. Isn't it that what we proved before? Q1 plus Q2 equal QS plus Q naught. Okay, that's all we did before. So we were at the same location than them. Okay, so we were at the same location as them before. We could have keep going with the same thing over here. We found that Q1 plus Q2 equal QS plus Q naught, so we could keep this one. So if you write this one, we are at the same point, no? All right? So let's see now what they did. So what happened now is that, okay, so you see we needed to divide this one by QS. So now I think that just like if you were putting the QS on this side, so if you want you could say this is equal to Q1 plus Q2 equal QS plus Q naught. So now if I take Q1 plus Q2 and divide this one by what? What are we trying to find? Q1 plus Q2 divided by QS, no? So we divide now that one by QS. What do we get? We get, let me just write it down, we get QS plus Q naught divided by QS. So this will give you that Q1 plus Q2 over QS equal to 1 plus Q sub naught over Q sub S. Okay? And let's say this is our expression A. I got it now. I don't know why I missed that step. You see, should have think about that step. So now, really, I'm going to do it a bit differently, okay, for the understanding. So page 106. So here we are now. All right, let me move to the left. Let me put my pens on this side. Okay, so what is important part over here to understand is that, which is basically what we're doing before. What is the efficiency for the power cycle? I mean, if we do it is work over what? QS, so this is equal to QS minus Q1, the same thing as we did before, divided by QS. Which will be equal to 1 minus Q1 over QS, but this is important part. Since everything is reversible over here, if they don't have the term reversible, this is not true. This is equivalent to what? 1 minus TD over TS, no? So now you can see that because of this inequality, this is the important part, guys. You can cancel the 1, no? You can cancel the minus sign. So basically we end up here with the relation Q1 over QS equals TD over TS, which is what they had over here on the solution. Let me try to do it a bit bigger. Maybe we can Okay? Is what they have over here, no? But they're not explaining to you how they got this. So the important part over here is how you got this one is because this is reversible, then the efficiency is directly proportional to the temperatures of the reservoirs. Okay? So if we do the same thing for the this is for the power cycle. What would be for the heat pump? I know we had different letters. What was, remember the letter for the heat pump? Was it gamma? Was it gamma? Okay. So gamma, I mean, we wrote it before, so I know you know it. So what is the efficiency for the, what do you get out of the heat pump? We get Q2. What do we need to put in? Work. Okay? So we get Q2 divided by what? I don't know, I wasn't paying attention. So we'll be Q2 hot minus cold. Yeah, Q2. So that's not the way they are doing it. And because this is reversible, what do we know? This should be proportional to what? So T2, Q2 comes from, so it's TD, no? So TD minus, honestly not, okay, so it's not the same as they were doing, so what can we do with this? So we're going to do differently than what they were doing. So what did they do there? Q2 over Q naught. So let's see, what can we do now? Yeah, but I don't understand this part over here. I don't know where they got that equation. I don't think that's correct. You see that one over here? Because they consider this one as being also a power cycle. That's good. We might get something different. All right, let's do it the way we think it is, and we'll find something. We're probably gonna have to turn around.
If you 1 over it, it's the same.
If you what?
If you 1 over both sides, it should be the same.
If you 1 over. I mean, say that again. What do you mean by 1 over?
Like Q2 over Q2 minus Q0, and then 1 over it, it should be the same as 1 over Q.
Ah,
over
okay.
T.
Okay, I know what you mean. So from here you say now that you could say that then that's probably the way. Q2 minus Q naught over Q2 is equal to, yeah, I see what you mean. TD minus T naught. So you take the inverse, no? That's what you say. Equal TD. So now you find that yeah, good point. So you find that 1 minus Q naught over Q2 equal to 1 minus T0 over TD. Which will give you Q naught over Q2 did I do something wrong here? they get Q2 over Q naught. Okay, so let's not follow what they do on the solutions. Let's be coherent with what we do. So it will be Q naught over Q2 equal to so will be T naught over TD. Okay. I rather don't think that's what happened to me when I look at solution. I get confused. So. Introducing equation C on the left of equation A. What is equation A? I have no idea. Right, let's not look at this. Looks like a lot of algebra. Let's not look at this. Let's try to do it on our own. Okay, so the equation A, I guess, is that one here, what they're calling about, but Q sub 0 over Q sub S guys, I need a bit of practice for this one. Let's get this done. So 107. Don't copy anything, okay? Let me just try to solve this one initially. So over here, what we have is Q1 plus Q2 over QS equal 1 plus Q naught over QS. Okay, so it looks like from this equation we can write Q naught equal to Q2 T0 over TD, and we have QS equal to Q1 for that, but it's good. That way you can also see that I might get in trouble, no? So here we already get something different. We get T0 over TD, no? Instead of TD over T0. So this is, we have a different. What I understand is this: by introducing equation C on the left side of equation A, so this is A, okay. So TD S oh, I got it now. No, I got exactly how they do it now. Okay, so, alright. So, don't copy anything. I will provide you with the class notes, but let's see. So let's see, I think what they did is this. Let's see if I understood. So basically what they say is that they take the energy balance equation, so using equation QS plus Q naught equal Q1 plus Q2, okay? So if we use those two equations over here, if we use that equation, what is Q1? Oops. If we use that equation, what is Q1? Q1 becomes QS TD over TS, okay? And now if we use this equation over here, what becomes Q2? So Q2 will be Q naught times TD over T naught, and this is what we have different than them, I think. So now when you come here, what they do, let's just rewrite this, so we get QS plus Q naught equal to QS TD over TS plus Q naught TD over T0. Okay? And now they combine those terms QS and Q naught on both sides. So we get, if you combine the Q sub S, what do we get? 1 minus TD over TS. And if we combine the Q naught on the other side, what do we get? So we're going to get TD minus T naught minus 1. And now is where we're going to use that expression that we got before that we thought we could not use, which is the Q. So now we write Q0 over cube S will be equal to what? 1 minus TD over TS divided by TD over T naught minus 1. And I will just finish here. I'm going to do all the algebra. So, how do we call this one? Let's just call this one B. Okay? And from these two expressions over here, Q1 over QS equals TD over TS and Q naught over Q2 equal to T0 over TD. No, that's not how to do it. Okay, sorry. Finally I got it, so sorry for that, guys. So it's not a good thing for me. So give me 2 minutes, sorry for that. So now, substituting into the equation. Okay, give me a minute. Which is 1? Q1 plus Q2 over Qs equal to 1 plus Q sub 0 over Q sub S, which was equation A. Alright? So this would be equal to what? 1 plus, I'll let you do the algebra, 1 plus 1 minus TD over TS divided by TD over T naught minus 1. Okay, so we're gonna say sorry for that, but at least you see that, okay, problems sometimes don't come right away, okay? We need some work to go around. Alright guys, so one thing, I'm gonna assign probably just 2 or 3 problems about this chapter, but I'm not gonna make the homework due next week because I'm gonna keep adding problems. So, but start working on this, okay? I'm just gonna select a couple of problems about this chapter 5.